Due to climate change, water is becoming a more scarce resource, especially in third world countries, where their infrastructure is not set up to deal with the growing population and the lack of water. According to OECD.org, 70% of the world's fresh water is used for agriculture. This is especially problematic in third world countries since they primarily rely on flood irrigation due to its low cost. The scarcity for water in agriculture can largely be dealt with drones, LiDAR, and 3D mapping. For my project, I set out on the quest to try to solve this issue. Most of the current research in this area doesn't deal with the flood irrigation. For this reason, it took me a lot of trial and error to figure out how to optimize a farm. The first step I took in experimenting on how to optimize a farm was building a small planter that would house 6 rooms. I used a drone-like system in which it would do scans and then run it through a TensorFlow model I built. My next iteration switched from only using photo data to using photo data in conjunction with LiDAR. I decided to use LiDAR after reading about the kinds of drones that are currently being used in agriculture. These drones typically have LiDAR sensors on them. I found it pretty easy to work with these LiDAR sensors, and since they're widely used in the field already, I wanted it to be easy to integrate, and that's why I chose to add LiDAR to my project. LiDAR stands for Light Detection and Ranging. How this technology works is it measures how long it takes light to leave the sensor and come back. It then uses this to be able to build 3D models of environments. Through using LiDAR, I was able to get a much better understanding of how the farm was functioning and where there were dead spots in the farm. However, LiDAR did have its drawbacks. It wasn't until I included a leaf area index algorithm into my project that it really started to work well. A leaf area index measures the distance in between leaves, and then it randomizes it to figure out how many leaves are on a tree. By being able to pretty accurately tell me how many leaves were growing on the tree, I was able to get a good sense of how well each of my plants were growing. After figuring out how to optimize the optical part of my project, I wanted to figure out how to streamline it. I ended up building a Firebase project which helped me streamline my project by allowing me to bring all my data into one spot. I was able to hook up my Arduino, my Raspberry Pi, my TensorFlow model, and my camera, all to Firebase. This made the project much easier. However, I still had one glaring issue with my project. Up to this point, the project only told you what areas needed watering, but didn't automatically water it for you. This meant that you still need to be using a fair amount of labor in order to water the exact spots that the system said needed watering. For this reason, I decided to build an automated floodgate that would automatically release water in only the areas that needed water. This component was by far one of the hardest things I've ever had to design in 3D print. Not only were the supports very hard to get out, but the design required every piece to be as optimized as possible, otherwise you get water leakage. My biggest issue with integrating my floodgate was having it not disperse the right amount of water. I primarily blame this on me not using linear servos. Linear servos would have made this project easier, but the wait time on them was too long, so I ended up settling for using traditional servos. Because of this, it made it hard for the gate mechanism to lift up and release the right amount of water. It took me many hours of testing with the servo and the sensors to figure out how much water needed to be dispersed. At this point in the project, I hit an area that one of my friends calls integration hell. I was unable to get my project to work seamlessly together on the first try. One of the biggest issues I was having was the Arduino wasn't working with Firebase. I ended up solving this issue by replacing the board. My other issue was having the sensor and LiDAR data work in conjunction with each other. I came up with something I call a health score. This score is based on 1 to 100. 1 to 50 being that it needs water, 50 to 75 meaning that needs a bit of water, and 75 to 100 meaning that needs no water or very little water. Though this method was a little crude, it allowed both sensors to work together, and I was able to get the watering mechanism to work properly. After all the integration was figured out, I was ready to start testing. I set up a planter with 3 different regions, one that used flood irrigation, one that used recycled water, and one that used my system with fresh water. My findings were that the one that used recycled water ended up killing my plants due to its high pH level. Though the flood irrigation system had a slightly higher health score, it used 5 gallons of water a day, whereas my system used 1 gallon of water a day and only was 4% less healthy according to my sensors. Furthermore, my system ran more times, running on average 6 times a day with an average 2-minute watering cycle, whereas the flood irrigation system ran for 30 minutes once a day. This was meant to mimic how farms work. Overall, this project was a success. Though my plants might have been slightly less healthy than flood irrigation plants, I used 4 gallons less of water a day. I think this is an overall win and would help fix the water crisis that is impending due to climate change. I hope to continue my work in this area by testing on real-world farms. I think this project could have a huge benefit to the world, especially in third world countries.